Welcome to Spectra Forge. In the series on applied digital signal processing, today we will look at Fourier transforms. In the world of signal processing, understanding or analyzing the signals in time domain is not sufficient. We perhaps have to look at another domain to extract the information. The domain is a frequency. And to understand or extract the information in the frequency domain, we need to look at Fourier transforms. Fourier transforms plays a key role, or plays a very critical role in understanding any signal. It could be a communication signal or a audio signal or image data for that matter. So Fourier transforms provide a mathematical framework to analyze the signals in the frequency domain. Analyzing the signals in frequency domain enables us with a smarter and more effective solutions. From designing audio equalizers to analyzing ECG waveforms or detecting faults in emissions. So the ability to work in frequency domain will be come in handy with with Fourier transforms. So why Fourier transforms? As I said, sometimes analyzing signals in time domain is extremely difficult and it's not just sufficient, and we need to look at another domain, which is frequency. So this is especially when the signal is complex and contains multiple frequencies or is noisy. So without additional tools such as the Fourier transforms, for example, it's hard to tell what frequencies are present and whether certain patterns are meaningful or they are just random fluctuations. So a well-behaved signal uh, can be decomposed into a sum of sinusoids. This is the principle behind Fourier transforms or Fourier series. Fourier series is mainly for periodic signals, and Fourier transform is for aperiodic signals, which we'll discuss that later. So when I say a well-behaved signal is the one that satisfies certain mathematical conditions to ensure that its Fourier transform or Fourier series exists and is meaningful. So some of the properties of well-behaved signal, some of the properties are should be the signal should be absolutely integrable. That means the total area under the signal is finite. It should be continuous, piecewise continuous, so that it can be differentiated or it can is integrable. And the variance of a signal should be bounded. It cannot be infinite, as in it should be bounded by a finite value. So these conditions guarantee that signal can be analyzed in the frequency domain, allowing us to extract useful information about its spectral content. So the Fourier transforms helps by converting the signals into frequency domain. So from frequency domain, we could analyze what frequencies are present, how strong each frequency is, whether those frequencies are steady or changing. So any signal can be decomposed as a sum of sinusoid, as I mentioned. So for example, if you look at a signal here, which has a cos 2 pi f 1 t and cos 2 pi f 2 t, and the x of t, the figure shown on the right is basically a time domain signal, x of t, and then you have in frequency domain, which shows the frequencies f1 and f2, and a naught and a1 are the coefficients, or in other words, you can see that as an amplitude. So when I decompose the x of t in frequency domain, i can get I can extract the frequency content, and also I can see the coefficients, which is the amplitude, how much the frequency, how much is a contribution from that particular frequency in the for the time domain signal. So here a naught and a1 are called the Fourier coefficients. We'll have look at this in more detail in the next slide. While any complex waveform can be constructed by adding sinusoids of various frequencies, amplitudes, and phases, working directly with sines and cosines quickly becomes cumbersome, especially when once you have introduced phase shifts or need to perform operations like convolutions and filtering. Sinusoids are intuitive for visualization, but the trigonometric forms makes algebraic manipulation and analysis awkward, especially when working with filtering or when you are doing a convolution in an LTI system. By representing a sinusoid as a complex exponential form through Euler's formula, things will be simplified. So, in short, complex exponentials are the language of, or the natural language of signal processing. It preserves all the intuition of sinusoids while unlocking powerful, elegant mathematics. So here, for example, if you replace the, where is my pointer? Yeah. So, if, for example, if I replace the cos and sine or the sinusoids with an e power j omega t, things becomes much simpler. So sine becomes e power j. It's a linear you can treat this as a linear combination of a complex exponential, where here the coefficients are 1 by 2j and minus 1 by 2j for sine, and for cosine you have 1 by 2 plus 1 by 2 again, 1 by 2 again for the two coefficients. So the x of t can be written as a linear combination. So it's a continuous signal, it's a periodic signal. So you replace that summation with an integration here, and x of f are the coefficients, linear coefficients. Here it is 1 by 2, for example. So it's a cos, then if it's only a cos omega t, then you'll end up with coefficients, two coefficients, for one for omega and another for minus omega, with coefficients being 1 by 2 for both. So x of f into e power j 2 pi, 2 pi, replace 2 pi f with omega, so you get e power j omega t into df. F is basically the frequency, so so omega is 2 pi f, so f is omega by 2 pi. So this is, so x of t now is now expressed as a linear combination, or integral of of complex exponential, where x of f is the coefficient. And similarly, x of f, basically the coefficients, the x of f are now the coefficients. This can be obtained by taking the inverse of this. So when I multiply this expression with e power minus j 2 pi f t, you will end up with x of f is equal to integral of x of t and e power minus j 2 pi f t multiplied with it, because e power j 2 pi f1 t and e power j 2 pi f2 t, if you have, I mean, they're orthogonal, so they both vanish, and you will end up with this result if you work out the math. So here x of t is the small x of t is in the time domain, and x of f is the coefficient is of the is a linear combination coefficient, and that's coefficient is in the frequency domain. And when I multiply with exponential of minus j 2 pi f t, I end up with this form, where now this is called the frequency domain. So this coefficient x of f is called the frequency, it's a frequency domain representation. So one is in time domain, the other is in frequency domain. So this is called Fourier transform. X of t in time domain. This is a capital X of f, which is the frequency domain. That's it. So when I multiply with e power j on x of f, I get x of t, and when I multiply with e power minus j, I end up with x of f. So that's the idea. However, by doing this analysis, by replacing the sinusoids with exponentials, the math becomes simpler, where it's now just a linear combination of complex exponential. So now time and frequency operations become algebraically simple, because you can switch from one domain to another domain easily, and this enables us to perform convolution, filtering, and any advanced modulations, for example, in communications, very smoothly and tractably. Okay. So there are many advantages of performing frequency domain on time domain signals. For example, many signals and LTI systems are easier to understand when viewed by their frequency content. Complex operations like convolution in time becomes simple point-wise multiplication of frequency domain, which will look in subsequent lectures or in the series that requires some knowledge on linear convolutions. So Fourier transforms expose exactly which frequencies a signal occupies and with what strength, critical for measuring bandwidth. So in some scenarios in communications, you want to understand how much of your signal is occupying the bandwidth, and how much is it leaking into the adjacent channels or adjacent bandwidths, so that it doesn't interfere with the other users. And it's also helpful in allocating the spectrum. If you have multiple users, you can allocate different bands to different users and perform spatial division multiplexing without any interference, basically. So, and you can also have an advantage in frequency domain when you do such certain modulations like OFDM or frequency division modulation, frequency modulation. So these are best understood and designed in frequency domain, because sometimes it requires shifting in the frequency domain, shifting the frequency components here and there. So having them in the frequency domain will be very convenient. So these are some of the advantages of frequency domain. There are many advantages out, other than what is listed here in other domains, like in image processing or in audio processing. The examples here I've showed are mainly for wireless communications, as that's my background. So here is a concise table of some of the most commonly encountered time domain signals and their corresponding Fourier transforms. So we have already discussed that x of n now it's replaced with a summation instead of integral, because I am discretizing the time domain. So previously it was t, now it is replaced with n, which is basically the sampled from, if you have an ADC, you take the real time signal, which is a time domain, and then you have an analog to digital converter, do some sampling at a particular rate, which we'll discuss it later. So then it becomes a discretized, and those samples are basically represented as n here, and x of n is a summation over this x of capital X of a, which is the coefficient, and it's multiplied with the x complex exponential. So it's a linear combination of complex exponentials, and when you multiply with e power minus j, you end up with the inverse Fourier transform. So you have Fourier transform and inverse Fourier transform. So the table here shows, on the table on the right, shows a concise table. I mean, the table on the right shows some of the most commonly encountered. For example, if you have a sync function in the time domain, it becomes a rectangular window, or a window in the frequency domain. And if you have a Dirac delta function, for example, it's an impulse, let's say it's a delta, I mean it's an impulse, so it will occupy the whole bandwidth. So you can see that if you have fewer taps or fewer samples in time, or then it occupies bigger bandwidth in the frequency domain, bigger, I mean larger frequency, in larger frequency basically, or larger frequencies. You'll have many frequencies. If you have a single time sample, you'll have multiple frequency points. But if you have multiple time samples, you will end up with a single frequency. So it's a reciprocal. So for example, if my noise spectrum is spread over the whole bandwidth, then I'll have in the time domain it's only a Dirac delta. But if I have a Dirac delta in frequency domain, then it will cover the whole time range. So there are some intuitive or some nice way of understanding through Fourier transforms, and you can understand how the frequency occupies the bandwidth, how it behaves in time domain. For example, sampling rates. If you have high sampling rate, it will occupy larger bandwidth, and for lower sampling rate, it will occupy less bandwidth, which we'll discuss that later. So, but here are some of the examples of Fourier transforms. It's taken from a standard textbook. If we work out if we superimpose, so if you expose this as a linear combination of sine complex exponentials, you will get those frequency transforms basically. Okay, now that we have looked at the Fourier transforms and how to switch from time domain to frequency domain, we will now understand how it is applied in real life and how is it useful through an example. We'll look at OFDM as an example. I know we haven't discussed OFDM, but people who do not know OFDM will look at this in subsequent lectures in this series. So for the time being, let's assume that OFDM is. I mean, the reason I considered OFDM is because it is the signal is modulated in the frequency domain, which completely relies on the Fourier transforms that we have discussed. Switching, because it requires switching from one domain to another domain. So we have x of k. So this is a signal. X of small x of n is the signal that is transmitted. But however, the uh, actual data is in the frequency domain. So x of k is our actual data. The x of k, as we know, are the coefficients. So the values of those coefficients are the data. So you have multiple subcarriers or multiple carriers. N is your frequency points, and you modulate those or multiply those complex exponentials with these x of k's, multiple x, I mean different x of k's, where different x of k's will have different values. That those values are the data. So that's an OFDM signal in a simplified way. So this x of n is passed through a receiver, so passed through the from the transmitter, and it is received back by the receiver. So in between there is a channel, that is the over the air channel, that will introduce the impairments or degradation, because it has phase, amplitude, and other things. It distorts the signal. So we want to remove the effects of those channel. To remove that, we need to design an equalization. So since the signals is in the frequency domain here, the x of k are the data here. So we want to remove or recover, I mean, we want to recover the signal x of k as is. So we remove the effects of h of k. So h of k is in frequency domain. So we need to do something in the frequency domain. How do we remove the h of k? By taking by applying a reciprocal of it, 1 by h of k. But what is h of k? H of k is by using a least squares algorithm. The simple solution is r of k divided by x of k, assuming the w of k, which is a white noise, is 0. So you get r of k by x of k is h of k. This is our estimate. Of course, the estimate is corrupted by the noise here, thermal noise at the receiver, which we'll look at that later, and which is not very important for our current topic. So once we have obtained the H estimate of H estimate in the frequency domain, now we need to we have to design or implement this in the time domain. You can ask that, I mean, it is possible to do it in the frequency domain itself, but because it's sometimes convenient to do in time domain, it's not always a frequency domain is useful. Sometimes, when you're dealing with everything in time domain, it's sometimes easy to implement the equalization in the time domain. Okay, now that we have the channel estimate, so the equalizer would be the reciprocal of that. So for example, if you have the reciprocal of that would be 1 by h estimate x of k by r of k, which is again in the frequency domain. Once we have obtained the frequency domain of its equalizer, we need to implement that in the time domain, because as I said, time domain is sometimes useful when you have fewer taps. So to get the time domain channel equalization coefficients, assume that we have, not assuming, we have estimated channel and then take the reciprocal. So now we have the equalizer. So we plug that equalizer coefficients in the expression. So this is h of f1, h of 2, so h of f2, h of 3. So the f1, f2 are the frequency points. So we have a bandwidth where we let's say if you have 1 megahertz bandwidth, you divide the bandwidth into different frequency points, or depending on the resolution that you want. So if you have a 1 megahertz bandwidth, and you can have a 50 kilohertz bandwidth, points resolution. So you'll end up with so many points. So these are f1, f2 corresponds to those points. So you plug those values in this the from the estimate, and then apply IFFT on this. So you end up with the time domain samples. So this is basically a linear combination. If you look at this, h of f1, f2, f3 are what you have obtained by this by applying or by employing the least squares algorithm to get the equalizer in frequency domain. And there's a linear combination of that is basically the corresponds to one time sample. And when you apply IFFT with endpoints, you end up with n taps. So these taps corresponds to the equalizer. So how many taps, how much resolution, I mean, how do you decide the number of taps, and how do we how many observations are required to get a good resolution? We'll discuss that in the next tutorial or next lecture in this series. So once we have identified these channel tabs, we implement this in the time domain, and then you get the equalized channel. So the effects of the channel will be removed in the frequency domain, because our the OFDM signal is in the frequency domain. So the when you take the FFT of this signal again, you will get the H of F, and when you multiply that with the channel response, it will mitigate, or it will completely nullify the effects of that. So yes, this is the example. So if, for example, here I'm showing you an example of the equalizer. So the blue line here on the figure on the right side shows the measured, I mean, shows the channel response of the, let's say, over the air channel, and we want to intentionally introduce a slope, like a linear slope, something like this on the red line. So for that, what we do is you note down the frequency points of each at each frequency point. Note down the values of the each frequency points and apply IFFT on these points. So you will get the number of taps in time domain. So you don't get the number of taps, or you will get the time domain response of the channel, and then you apply those taps in the time domain equalizer to get the desired response. So the number of taps, whether it's 11 or 13, 17, 19, I mean, it could be, 100, 101 taps as well. We'll understand how how the number of taps is chosen. This number of taps should be chosen very carefully, and we'll discuss that in the next lecture. However, so once we have obtained the channel taps or the time domain, the taps is basically means time samples, timestamps, discrete stamps, timestamps. So it's another word for time samples. Okay, so we'll get a time domain signal by taking the FFT of the IFFT of this red line and of the red line and apply them. So to validate that, I have also uh, conducted an experiment with those taps, with 11 taps, and I have got roughly, or not roughly, actually it's more identical to the red line. So the simulated is the red line, and the figure on the left shows the measured data, and on the right figure the blue line is the measured data. So we see that how the Fourier transforms helps in getting the frequency response we want. So the red line is our desired frequency, and that is what is depicted here. So this is a simulated model, and this is on the left is the actual measured value. So yes, so we have. I mean, this concludes our Fourier transform and its usefulness. So we have learned how to switch from one domain to another, from time to frequency, and how, I mean, useful it is, and why it's essential in some cases, and why it should be, why is reversing or switching from one domain to another is critical. For example, in OFDM, we switch from time to frequency and frequency to time, and for because of the sake of convenience. Uh, so yes, that concludes this lecture in this series. And if you have any questions, please post in the comments. And yes, please subscribe to the channel for more updates. And if you are interested in any topic specific to signal processing, please comment on it. I'll answer that, or I'll try to upload the video in sometime in the series. Until then, thank you. Bye bye.